Welcome everyone. My name is Ivica and I'm going to talk today about instruction level parallelism. So this is going to be an interactive session. So I'm going to ask you questions and I hope you will answer. Also, you'll also have some time to think and maybe let's talk a little bit. So it's not going to be like a traditional session. So feel free to participate, feel free to join in, also the little girl. So let's start. So I want to introduce instruction dependencies. So what are these instruction dependencies and why do we care for them? Well, if you have like in your program, you have two blocks, block A and block B and block C, three blocks, block A, block B and block C. And block B depends on the results produced from block A and block C depends on the results produced by block B. Then you have this chain of dependencies. And you need to execute first block A, then followed by block B, followed by block C. The same applies. Okay, so another thing is that imagine that block B takes 2 seconds, but you can completely fix the time needed to run block A and block C. Your program will nevertheless run 2 seconds because the block B becomes the bottleneck. And this is the talk about instruction dependencies. This is dependencies in real life, but also instruction dependencies are similar like this. Now, the modern CPUs, they can execute more than one instruction in a single cycle. So it can execute, like, say, 3 or 4. Your CPU is always picking up 3 or 4 or 6 instructions from the instruction stream. And it can also execute instructions out of order. So out of order execution means that it can skip the instruction that it cannot execute. But there is a limit to how much work a CPU can do. Regardless of all of the tricks that CPU tries to do to execute as much work as possible so it gets the best performance as it can. Now, when we say instruction level parallelism, so inside your code, your segment of code, your piece of code, there is a certain level of parallelism available, and this is the property of the code. This is not property of the architecture of the hardware. This is a property of the code. And the hardware tries to extract as much parallelism as it can. Now, depending on the codes, some codes have a lot of instruction level parallelism, other codes have very, very little instruction level parallelism. Here one example. So this is a function called cosine, and you see here certain statements that you need to calculate this cosine. Now, this function gets the argument which is x, and then it tells you it multiplies x by TP, and then stores the result. And then it calculates TMP equals x plus 0.25, and then stores the result. Now, if you look at this statement, you see that some statements depend on the previous statements. So, like, for example, this statement x equals x minus TMP depends on the previous one, which is 0.25 plus TMP. And that one depends on the previous one, and that one depends on the previous one. So each instruction has the input values and output values. And instruction can only execute if all the input values that it needs are available. So if you have an add instruction, which has 2 inputs and 1 output, both inputs need to be present before the CPU can execute the addition operation. So what this instruction means in practice for us is that we can have as much silicon, we can use all the silicon in the world, and we can use all the resources, the best CPU that we have. But what actually limits the performance of the software are these little arrows that go back. So this is the instruction. This is the dependency chains. And whenever you're working with any kind of parallelization framework, like vectorization, like multi-threading, like GPUs, like whatever you're doing, what limits you are the dependencies that exist in your code. Okay, now a small quiz time. We're going to do a thought experiment. So imagine we have a machine that has endless amount of resources. It has unlimited amount of memory loaders, unlimited number of adders, of multipliers, unlimited amount of every possible hardware that you can have. And we want to simulate in our brains how much time does it takes to execute a certain loop here. Now, each operation takes 1 cycle, except for memory loads and stores that takes 3 cycles. So how many cycles does the machine need to execute following operations? Now this is the first operation here. So it's a very simple loop. C of I equals A of I plus B of I. Now if I convert this to some kind of pseudo assembly, I get something like this. I load from A plus I load it to a register. Then I load from address B plus I to a register B. I perform the addition, A plus B to C. And then there is a fourth instruction which stores the results, CV to C plus I. So total 4 instructions. But the question is, even with the unlimited amount of hardware, how much time would this instruction need to execute?
7 seconds?
So, in cycles.
7 cycles?
Yes. So 6 cycles, let's say a little bit more. But what's the idea here? We have n instances. We can run these n instances, this loop, which is in a loop. We can execute all n instances at once. So like if you have a million instances, we execute them all in parallel. We can execute a whole loop in parallel, and we get it like 3 cycles plus 3 cycles. So there is dependence. So these two are independent, A and B load. They can be executed in parallel. Just a second. And then they take 3 cycles plus 1 cycle here, 4 cycles plus 3 cycles here, so it's 7 cycles. So you were right. Yes, question.
What if A, B, and C overlap? Like how does the hardware know they don't?
Sorry, can you repeat?
How does the hardware know that A, B, and C don't overlap? Because
No. So so there are details to this which make the story much more complicated, but. Let's assume they don't overlap, okay? Okay, so this was the first example. The whole loop, regardless if it has 5 iterations or 5 million iterations, executes in 7 cycles, yes?
And then the line 3 there in the for loop, whenever you, after the addition, and storing to the CV, I mean, wouldn't it take like 3 cycles to,
Yes, it would.
right? Like, then, so 3 cycles, first 2 lines, right?
The first 2 lines, A and B can be executed in parallel, 3 cycles.
And then you operate the plus
Yes,
A plus B.
that's 1 cycle.
1 cycle.
Yes,
And then storing to the CV.
yes, 3, another 3.
And then store the CV to C plus I. Another 3 cycle,
Yes, another 3 cycle.
right? And total of 10 cycles. Right?
No, where did you get the 10 cycles?
The store to CV is part of the add, right? That's so storing the result AV plus BV is part of that single cycle.
So this one starts to execute after 4 cycles. So the store starts to execute after 4 cycles, and it's done in 3 cycles. So at the end of 7th cycle, everything's done.
I was asking, like, okay, I understand there's 2 lines and AV and BV loaded.
Okay.
Takes 3 cycles. But the line 3, first,
This one.
yeah, the right hand side, AV plus BV takes 1 cycle. That's
Okay.
port. And then storing to the CV.
Storing to register is 0 cycles.
Okay.
So it's a register, it's not a memory.
I see.
Yeah. Okay. More questions?
no, I wanted to answer that.
Okay. Okay. Okay, so this is the next loop. So what changes here is that we have again a loop which goes from 0 to n, but this time we have a of I, and we are adding it, reducing it to this variable sum. So here is the assembly code. I load a plus I to this register, so loads 3 cycle, and writing to register doesn't cost anything. And then I add it to sum v. And then I unrolled this loop 2 times to make it clearer what happens here. Then I'm again loading a plus I plus 1 and storing it to sum v. Now, how much time does this need to execute?
N times 3.
Oh, it's okay. So, n times 3. It doesn't need to be exact result, just to be like an order of magnitude. But yes, why does it have to why does it need n times 3 to execute?
Because there's a dependency.
Yes, there is what kind of dependency?
I don't know.
But you said it, come on, you gave a number. Why did you give that number? Does anybody else know? Yes?
To synchronize on the sum.
Sorry?
It has to synchronize on the sum on every iteration.
Synchronize. So there is a dependency change on the sum. So to do this addition, you depend on this sum, which is calculated in the previous iteration. And I intentionally unroll this 2 times, so you can see this dependency here. And there is also dependency on the previous iteration of the loop. So you have a dependency chain that goes from the end of the loop to the beginning. It goes up, 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 up. And so the time that limits you here, it's actually the time you need to do this addition. You can do all loads in parallel. You can do n loads in parallel, and it takes 3 cycles. But this addition takes 1 cycle. So you do all loads at the beginning of the program. You need 1 million registers, you load them all, and now you just need to add them. You need to go through them, and it takes about 1 million plus 3 cycles. That's how much it takes. Okay? Okay, this is a second example. The third example, so this one. So this is a reduce on a linked list. So what does it do? So it goes over the linked list while the current is different than null pointer. Sum plus equal current arrow val, and current equals current arrow next. So this is the assembly. So I have 2 registers. One holds the sum, and one holds the pointer to the current. And then I load the current, which is, I load the value of the current, which is load current plus offset of val. So I load this value to this register, and I add it to sum. Then I load the offset of next, I load the pointer of next, so that's the next pointer. And I'm checking if current equals 0, then I break, and then I repeat the same thing here. So I have this load here, and this sum here, and then a load of the next value. Now, how much time do you think this needs to execute? Yes?
It's the same, basically, it's scaling linear over the size of our linked list plus some load that can happen in parallel because we have the same dependency over something we were summing up into the same register.
Yeah, so we are summing to we have a register chain that's related to summing. But what's the key difference between this example and the previous one?
There is also a dependency on the current loading, because the next current load is based on what the current.
Yes, the previous one you could do, so what he said, in the previous example you can do all million loads simultaneously, and then you could do the summing. Here you cannot do that. You need to do the load, because to do this sum, so to do this second sum, you need to current value of 2. But to get current value of 2, you need the value of current. But to get the current, you need to load the current, which was done in the previous iteration. Now this time, in this case, you get a dependency chain which depends also on the loads. And these kind of dependency chains are more expensive, because now the time you need to execute is actually, you need to do the load, which is 3 cycles, and then you need to do the addition, which is 1 cycle, and then you need to load the value of the current, the new current, which is again 3 cycles, and then you do that 7 cycles times 1,000,000 times. Example, if you have 1,000,000. Yes?
You can do the second load and the add in parallel, right?
Yes, yes, yes. You can do this sum V and current, and the CPU will actually do it like that. So it's less. Yes?
I think it's even worse, because you have to go through the main memory and not through the cache prefetch.
That's another thing. The topic of cache efficiency is a completely different topic. Let's assume it's 3 cycles, like everything is in cache and everything super fast. That's a completely different topic. Okay, so we know some news. So we say this kind of loop, this kind of code has low instruction level parallelism. And actually what's really interesting, I compiled this program, this kind of code with optimization level 0 and 03. And the difference between 0 and 03 was about 1.4 times. But if you compile this example with 0 and 03, the difference is about 10 times in speed. So you can imagine that all the instructions additional that the compiler generates don't matter because of this instruction level parallelism. Okay, so the first loop had no loop carry dependencies, so it was essentially executes in constant time. The second loop had loop carry dependencies, but not on data loads. And this was nice. And the third loop had loop carry dependencies on data loads, and it had very low instruction level parallelism. Can you guess what other types of code typically have low instruction level parallelism?
Anything
Yes. So all pointer chasing codes, if you have binary trees, if you have in a linked list, you have a lot of collisions and you need to go through those linked lists and so on, they have. And actually, we'll see later, if you take a linked list and convert it to array and then you iterate over array, it's much faster.
What about recursions?
Recursions.
Yeah, which depend on.
Well, a binary tree, it really depends on the recursion. You can have more or less efficient recursion. You need to do the analysis. Like if you're looking at the binary tree visits with recursion, it will be slow because it's generally you are chasing pointers. But you can create examples of recursive code that doesn't have necessarily low instruction level parallelism. So if you look at the instruction manual that you get with your CPU, for each instruction, it gives you two numbers. So the first number is, let's say this instruction load 8 integers, so it's part of the vectorization framework in the CPU. It has a latency of 7. So latency means the time between when you enter the CPU, it starts executing in the CPU and when it's done. And it takes 7 cycles to execute. And there is another, is a throughput. And throughput is 0.33. This means that it can execute 3 instructions in a single cycle. So it can execute more than one instruction in a cycle, but under the condition that those instructions do not depend on one another. Yes?
This throughput is less than 1 because there are more cores in the CPU?
No, no. It's inside one core, but the CPU, modern multiscalar CPU, can execute more than one instruction in a single cycle. They can execute 3 or 4 or 6. Okay, so what's the deal with these numbers? Why are these numbers important? Well, if you have a code that is essentially doesn't have this instruction dependencies, then you are mostly limited by these numbers in throughput. So you can execute every instruction, 3 instructions per cycle, let's say 3 loads per cycle. But if your code has this instruction level dependency and they're very dense, so everything each instruction depends on the previous one, and these kind of codes are not that uncommon. So you're essentially limited to these numbers. So latency is what limits you. So you can execute one instruction every 7 cycles. The good thing is the throughput is almost always smaller than latency, so you can execute essentially thinking about instruction level dependencies and breaking them somehow actually helps performance a lot. Okay, questions? No? Okay. So how do we increase instruction level parallelism? So the codes that typically have medium or low instruction level parallelisms are reductions. So this summing to one variable or multiplying to another one variable, and also all the pointer chasing codes, linked list, trees, hash maps, graphs, whatever. Also, if you have like a long sequences of auto-generated code, so this code doesn't generally, you don't write it, but you have a function that's auto-generated, it has like 50,000 instructions, and each of them depends on the previous one. In that case, you also have this low instruction level parallelism and low dependencies and high instruction dependencies. Also, if you have loop with very large loop bodies, so loop itself might not have the loop carry dependencies. Everything's in the same. Everything executes in the same without loop carry dependencies. But if the body of the loop is really long, and you have inside that body, you have this loop carry dependency that can also actually slow down your code. So if you want to increase available instruction level parallelism, essentially you have 4 techniques. One is that if you have a dependency chain, and this is what limits you. What you can do is actually interleave 2 dependency chains. So it executes a little bit of this one, then a little bit of this one, a little bit of this one. So you're interleaving them and you're increasing the available instruction level parallelism in your code. Then the second approach is you can shorten your dependency chains. So you can, instead of having dependency chain which is 1 million, you can have dependency chain which is only 500,000, and this will also improve performance. The third thing is you can decrease the number of times you need to iterate a dependency chain. So for example, sometimes you can iterate the same dependency chains over and over like a linked list or a binary tree. And if you figure out a way to decrease the number of times you need to iterate, that can actually really be helpful. And finally, you can break dependency chains. So this is the completely removed dependency chain with some kind of techniques, and we'll see what kind of techniques are used. Yes?
So how do you actually measure the length of a dependency chain? I mean, not manually.
So there is no, I didn't find in the literature any like a number which tells you like this instruction has this amount of instruction level parallelism and this one doesn't have another. There are some tools that you can do that, and they give you some numbers, but you need to sit down and think about them and see how that fits into your story. Okay, so here is an example of interleaving dependency chain, and this is probably the simplest technique. So I have this cosine function originally, which was really had a really big dependency chain from beginning to the end. And now I have a cosine function here, which accepts not one double, but two doubles, and returns two results. And now I am what was originally one statement, now it's two. So I have x times tp, and I have x first times tp and x seconds times tp. And I have here x equal x minus double 25 plus std floor, and I have x1 equals x1 minus double blah, 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 and x2 equals x. So there are two dependency chains. So one statement belongs to one dependency chain, and the next one belongs to another dependency chain. And there, this is the so-called interleaving. So this is the simplest technique, but it actually works really nice. So here I have here an example of nested cosine. So this cosine is like big, but actually it's not that big, about 100 instructions, and the CPU can have on the fly like 200 instructions that are waiting. So it's not that big of a deal. It's more big of a deal for embedded system where these buffers are smaller, and it can hold fewer instructions in flight mode, so partially executed, and then this would make more sense there. But here I have the experiment of nested cosines. So cosines of the cosine, and there is this parameter called recursion length. So recursion length can be like 1, 2, 3, 5. So 5 nested cosines, 7 nested cosines, 100 nested cosines. 100 nested cosines is already a very formidable dependency chain, which can be like 100 times 100, it's about 100,000 instructions. So it's a really big dependency chain. Now the question is, what we want to compare the performance of the left code, which has only one dependency chain, and on the second right side there is a two dependency chains that go interleaved. So how does it look like? Now I measured this on two places. So on a desktop system and on embedded system. Desktop system was my CPU from this laptop, so it was like Intel i10. 10th generation Intel i5 core i5, and embedded was Raspberry Pi. So what you see here is that for the desktop system, so this is the ratio between the system simple versus interleaved. So this is the simple version and this is the interleaved. And this is the runtime ratio. So how much time does it take to execute it? And you see here that for the desktop system, it slowly goes up and reaches about 0.7, 0.8, which is some kind of line after 42 nested cosines. But for embedded system, it quickly goes up after 2 or 3 nested cosines, you're already 1.6, 1.7, the speed up you get from the interleaved version compared to the simple version. Yes?
What does the recursion size mean? Is that the amount,
that's this
of interleaving we're doing? Or?
No, this parameter.
Oh, okay.
This is the parameter, recursion length.
Yeah.
So this is recursion size. Yes? Yes?
Was there a reason I would have written it to pass a pair? Because the values of the pairs, you don't really, they're independent of each other, right?
Yes, they are independent. These pairs are complete.
Just call the normal function.
You can do that also. You can do that also. It was I liked it this way better. Okay. So can we do interleaving with a linked list or interleaving with trees? Yes?
I would say it depends kind of operation. Like for a tree, depending on if it's a binary tree, you might go both nodes interleaved, or we might have multiple trees or multiple lists we do our operation on. Depends on the context if that makes sense or not.
You can do.
You have one tree.
You can have one tree and do interleaving on that one. So you imagine you do two lookups in the same tree. So you're doing a little bit of the first lookup and a little bit of the second lookup. So with linked list, it's simpler because you're always in the same node. Look, you have 10 lookups in parallel, going over linked lists. You're checking, you get 10 values and check on the linked list node 0. Then 10 nodes check on the linked list node 1 and so on. So this is the interleaving on the linked list. Trees is a little bit complicated, more complicated because for each value that you're looking up, you need to have the current node there. So you need 10 current nodes. Yes?
When I say interleave, do we say that we split into two pair?
Yeah, 2 or 3 or 4 or 5.
It depends. But I expected to, for the before slide, it should double the, performance, but it doesn't.
Well, it was interleaving only 1 or 2. So the experiment here was interleaving either 1 value or 2 values. But you can interleave 4 values. That's not a problem.
But we parallel, because we pair it, so they will run in parallel, I think. So it should double the performance, right?
It's all, yeah, okay. So yeah, so in the one thing, in certain sense, yes. That's what you would expect. So you would expect that this line is not 1.8, but it's 2. But interleaving also adds a certain overhead. Because you have more instructions, well, for example, maybe register spilling, the compiler is not doing really, so it's more difficult to optimize this code than this code. So there are additional factors that slow down. Maybe also the data doesn't come as fast as it was coming earlier. When you do interleaving, you're putting more pressure on the memory subsystem, so it needs more memory from the data, and that can also slow it down. So there are several factors that you don't get perfect speed up. Interleaving dependency chain, so if you have n linked lists, so you have several linked lists, you can do run lookups on 4 linked lists simultaneously. In trees, you can, instead of doing one lookup, so you take a node and then you're going through the tree, you can take several nodes, several values that you're looking up, and then you can do parallel lookups in a binary tree. So how does that look like? So here is the code. So what happens if, let's make it very simple. So let's say you want to look up two values in parallel. So you're starting from the root, and then you're moving down the bottom of the tree. So the paths for these two values are not necessarily the same. So you will need 2 current nodes, and they're gonna move through the tree independently. And you see here that I have, for example, if I have n lookups, I was doing n parallel lookups. So I'm looking up 1 million values in a binary tree, and I'll do them all in parallel. So I have this outer loop which goes from 0 to n, and then the current node, which was originally just 1 value, is now an array. And then I'm going over the binary tree first on level 0, then on level 1, then on level 2, and going down, 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 down until I find all the values that I need. And here is the result. So time needed to perform 16 million lookups into a binary tree, depending on a binary tree size. And you see here runtime here. There is a simple runtime, so the simple algorithm, and there is a parallel interleaved runtime. So when we're doing 16 million parallel lookups. So how does it look like? When the tree is small, we have these memory caching effects, which there is not that much difference. But as the size of the tree becomes bigger and bigger, then you see more and more of the difference. So if, for example, for the 16 million lookups on a tree which has 16 million, which is 16 megabytes, we have about 26-7 seconds, and the simple is about more than 50, like 52, 3 or 55. Okay? So this is interleaving is the simplest, most straightforward technique. And it works if dependency chain is long enough. Sometimes you don't have stuff to interleave. You are just looking up one value, and this creates a problem. And the second thing is this increases register pressure. So registers in the CPU, there are a limited number of them. So let's say 16 or 32 registers. And if the original code needed 8 registers, the new code will need 16 registers, and you might be out of registers, and then you need to spill values on the stack and so on. So it makes make this optimization less efficient. And that's it. Question?
I would also say it significantly reduces the readability of the code.
That's completely. I agree completely, but it's. There are other people who are responsible for readability of the code. Like when you're doing performance, you always end up with some kind of mess.
No, I mean, there are better data structures to do that.
Yeah. Okay. Okay. The next thing is to shorten dependency chain. So it would mean like normally shortening means like breaking it into two and then interleave them together. Ideas about how would we shorten this dependency chain?
You can use smart summing algorithm. You don't need to sum it linearly. You can do some tree reduce and get much better results.
Yeah, you can do that. Actually, that would work. But in the context of parallel algorithms, that would make a lot of sense. But in the context of our things, it would be like overkill because that code would be really messy. Can we do it simpler, more simply? Yes.
Having to part sum more part sum variables that we sum first and then we sum.
Yes. So having more than one sum. So we have partial summing. So you have instead of sum, you have one sum, you have four sums here: 0, 1, 2, and 3. And then sum 0 plus equals a of I, sum 1 equals a of I plus 1, sum 2 equals a of I plus 2, and so on. And then at the end, you sum all these four sums into one big sum. Now the compilers actually do this. Optimizations for integers, and we compile with those three. They don't do it for floats, because when you change the order of summing, you're actually changing the way the results a little bit, because floating point is not perfectly associative, and then the compilers omit that. But if you put to the compiler like f associative math or f fast math, it will also work. Yes?
This crashes if your n is not divisible by 4.
Yeah. Of course, you need to deal with that one also. Yeah, there isn't enough place on the slides for that one. Yes?
You're mentioning vectorization intrinsics here as well. How does parallelization between vector instructions and the regular instructions, like, can the CPU do both of them at the same time?
Yes, with just instructions, you can do whatever you want.
And actually, if you're trying to vectorize the whole stuff, it looks exactly like this. Like, you just take the register set to the left
Exactly,
side,
yeah.
you just load them, and then, for example,
But I would put the story of factorization for some other time, because we don't have enough time to cover everything. Question?
I just wanted to ask could you run a vectorized one and a normal one together?
Yes, you can do, instead of 4 regular sums, you can have 4 vectorized sums.
Yeah, but I mean, like, have a vectorized one and a individual one, so you get 5 elements, and then interleave those.
You can do that, but I don't get what would you get from that. So I didn't do these experiments. The experiment was done, the guy from the Algorithmica, Sergei Slotin. I really recommend this site if you like to read about algorithms and optimizations. So originally it was 15 gigaflops. Gigaflops is gigafloating point operations per second. And when you have 2 copies of counter, it's 22 gigafloating point operations per second. And this is what he was actually measuring. So it was a bit similar, not exactly the same. So look at this code. If you look at this code, where is the dependency chain at? Is it on this A of A equals X? Can you do this in parallel?
Yep.
Can you do all of them in parallel? Yes. So it's the dependency chain on the addition. Questions? I saw some raised hands. Yes?
So, just to paraphrase this, make sure I'm understanding this right. So you are batching as many parallel operations you can do, which might be expensive, and then you have one accumulator which you just accumulate at the end.
Yes. So the CPU will do, let's say, 200 or 300 or 500 parallel of these operations, but he will the addition, the summation, the accumulation will be done sequentially. Okay, can we shorten dependency chains with linked lists or trees? Any ideas? How would you make a binary tree shallower.
Rebalancing.
Rebalancing would do, and that's why axial balancing makes sense. Sorry, yes? Yes, yes. Okay, yes?
I mean, you can also just flatten the whole binary tree and trapezoid and have that be a representation. There's no need to have it in a node-style representation.
Yeah, that's not shortening. I wouldn't call that shortening. Just make it shorter. But the thing that you propose is actually what's normally done. So instead of having inside a single node, having one value and then left and right, you can have 4 values and then you have 5 pointers. Yeah, 5 pointers to left, right, and so on. And by doing that, your tree becomes shallower. These operations that you're doing at the inside the nodes are actually cheap, and if you're using vectorization, you can actually process 5 nodes with 4 nodes with a single instruction. So in that case, in terms of instruction count, doesn't matter, but you have fewer pointers to chase. And with linked list, the same idea is essentially. So instead of storing 1 value in a linked list, you would store 4 values in a linked list, or 8 or 20. Yeah. Questions? Yes?
Linked list, if you do a sum, you could also store a pointer to the middle of the list and a pointer to the bottom.
Of course. If you know that your value is in the second half of the list, you can just spring. But I wouldn't call that instruction level parallelism. It is, but you're actually executing much fewer instructions. Yeah. So here is an example of linked list, which has total 4 nodes in a single node, and you see here that when you're going over this one, it has really inside the node you have really good instruction level parallelism, but when you're jumping over this, then it's not that great. Okay, so the next technique is to decrease number of passes. So the dependency chain remains the same, but instead of passing through it x times, we pass through it smaller number of times. So how would that work? So if you have a linked list and you're looking at n values, and these values are stored in vector in a linked list of size x, you invert the lookup. So instead of looking up values from the vector inside the going over linked list and taking values from the vector one by one and going over the linked list, what you do is that you take values from the linked list and then you're going over vector. And that's diversion, because going over vector is much more efficient than going over linked list. So instead of going over the linked list n times, you're just going over it once. Yeah. And the last thing is breaking dependencies. This is more difficult because it requires a design, some kind of a design. And how does it work? So you need to sit down and think what is in your case. I have 2 examples here. One is for linked lists and one is for binary trees. So if you have a linked, you're looking up n values in linked lists. So how do you do it? In the first pass, you go through the linked list only once, and you create an array. And each value in the array points to a node in a linked list. And when you're and the second pass, instead of going through the linked list, you're going through the array. So what happens then? The thing is, when you're going over array, instead of going over linked list, you can do all loads in parallel. And CPU can execute many loads in parallel. This is not possible with linked lists. The second way to do, you can also take a linked list and create a new vector and just copy values from the linked list, and then you're going over vector. Of course, this makes sense. There is certain overhead with this one. It makes sense only in cases when you will be going over the same data structure several times. Yes?
20 minutes.
Oh, 20 minutes till now. Okay. The second way to do it is use in-array trees instead of pointer trees. So if you remember, there is a way to represent trees with an array. So imagine you're currently at node is x, and you want to go to the left one or right one. So the left one, the index of the left child is 2x plus 1, and the index of the right child is 2x plus 2. And this is how you would break. Instead of chasing pointers, you're doing arithmetics, but you can do arithmetics in advance than you can do. The CPU has more tricks in its sleeves to do arithmetics than to chase pointers. And here's the example. So this is a lookup, time needed to perform 16 million lookups into a binary tree. And the blue one is pointer-based runtime, and the red one is array-based runtime. And you see here that up to about 256 K size of the tree, they're about the same, but then they start to, the difference starts to be bigger. And if you're working with a very, very big array, you see that here it's about 20, 30 seconds, and here you're about maybe 80 seconds, so it's quite a drastic difference. Okay. So we have 20 minutes until the end. Let's do this one. So compilers, in-order processor, instruction level parallelism. So until now we talked about out-of-order processors. Well, out-of-order processor, what's the deal with them? Out-of-order processor starts executing instructions, and it comes to instruction that it cannot execute because the operands are not calculated yet. So what it does, it just skips over it. And all server system, all desktop system modern are out of order, and some embedded systems are also out of order. But there are certain embedded systems that are in-order processors. These processors are simple processors, but there is a deal with them that they cannot skip over instructions that are stuck. And we need to figure out what to do with those. So for in-order processors, even the short dependency chains are a problem. And the thing is that these optimizations I'm going to go about now, you cannot do them in C++. You would need to do them assembly, because you cannot control how compiler schedules instructions from a high-level languages like C or C++. Yeah. So what's the problem? The problem is the data for the current instruction is not there, and processor has stopped. It cannot do anything. It needs to wait for this data to come before it can move on. So here is an example. On the left, I'm loading A, B, and C, and calculating C equals A of I plus B of I. If you remember, that was the first example. I have two loads of A of I, B of I, and then I have C of I. And C++, and then I'm storing, so I'm doing this addition, and finally I'm storing the result to this memory address. And one of the ways to fix this is to unroll the loop, and then to interleave the more iteration to help break dependency chains. So I have dependency chains from C to B, and I have dependency chains from store to addition. So I have from addition to loads, and from the store to addition. So what I do is first I unroll the loop. So I repeat the loop body 2 times. So you just see the same T here on the left, so I just copy 2 times. Here's the second time. And then I interleave my data. So I have these 2 loads belong to iteration 0, but these 2 loads belong to iteration 1, and this addition belongs to iteration 0, and this addition belongs to iteration 1, and this is from iteration 0, and this is from iteration 1. So what happens here is these first 4 loads they can execute, there are no instruction dependencies between them. So the first 4 loads. There is dependency here, but between this addition and dependency, it depends on this B, but this B is actually, there are two instructions between them. So you have more instruction level parallelism, and there is the CPU will be stalled for less time. So when you get to executing this addition, there is some chance that both of these loads A and B will be completed. And same here applies for stores. Of course, you can unroll it more than 2 times. You can roll it 4 times and then interleave 4 iterations and run them at the same time. And compilers actually know this, and this is compiled with the O3 Clang 16, O3 architecture Skylake, a little bit old, and you get these 4 interleaved iterations. So when you're programming using vector intrinsics, you will want to do this optimization manually. So what is the problem is, there is of course problem with this one, is that you have unbalanced use of resources because you have 4 loads running at the same time, and inside the CPU there is a limited number of loads that it can execute. So it's putting more pressure on the memory, on the CPU's internal resources. But for in-order CPUs, that actually might make sense. Again, you have the problem of increased register pressure when you're doing loop unrolling and interleaving. Yeah, so that was one technique. The second technique is called loop pipelining. It's more complicated, but it uses resources in a more balanced way. So what's the idea? So you take the loop, you split the loop body into several phases, let's say phase loading, phase operations, phase storing, and then you execute, let's say, phase 1 from iteration 0, phase 2 from iteration 1, and phase 3 from iteration 2, and you get something like this. So here is example of loop pipelining. Again, the same example we had earlier. And look at the loop. So this store belongs to iteration 0. This addition belongs to iteration 1, and these two loads belong to iteration 2. And you see here that this is I plus 2, I plus 2. So I have some preparational step before the loop, and at the end of the loop, I have a few steps that I need to do. But what happens here is that you don't have, this addition doesn't depend on this store. And these loads, they don't depend on this addition. So you have, this is really nice because the CPU has a lot of available instruction level parallelism, but this is really complicated and compilers can do them, and embedded compilers actually do something like that. If you're gonna write codes for embedded system, then you should know this technique. Okay, any questions? How much time do we have?
13 minutes.
13 minutes, okay. When it comes to tools, I hope until this point you have developed a certain gut feeling or hunch for instruction level parallelism. You, at this point, at least we talked and I saw that you participated, that there is sometimes the problem is instruction level parallelism, and then you need to think about how to solve that kind of problems. When it comes to tools, they aren't that great. Intel has this top-down microtexture analysis, which tells you what percentage of cycles was spent because the CPU wasn't getting data from the memory, and what percentage was spent in waiting for the branches. But the problem with this approach is that it doesn't tell you exactly. So you have like, it was spending 20% of the time waiting for the data from the memory, but because it was waiting from the data from the memory, other instructions couldn't execute, which was on that dependency chains, and so it's all messed. It's messed, and you don't know exactly what was going on. If you can analyze instruction level parallelism on assembly level. This tool is called LLVM MCA, but you need to take assembly, which means that you're actually limited to the size of the assembly, because assembly very quickly grows. So for small loops works fine, but for bigger loops it doesn't look that great. Now I have an example here. This is my loop, and the Clang produced two versions of those loop. One is where the loop is very simple, and the other one where the loop is unrolled. And the unrolled version is about 15% faster. And here is the assembly that it produced. Now, I don't expect that you're fluent in assembly, but let's go over the instructions. So this is the first version. So this vmove DQU, it just loads data from these memory addresses from A plus A of phi to register YMM0. Then you have this VP add, which adds data from UMM0, and it loads another data from B of I. So this is loading of AI, and this is loading of B of I and adding it to a register, to A of I. And the third instruction is the store instruction. So it takes UMM of 0 and it stores it to this pointer, which is RDI plus R9. R9 is I, so the iterator, and RDI is the base address of the C register. Then R9 is I, and it adds 32 to it, so it's the increment of the loop. And then compares if R9 and R8 are the same. It checks if the loop is at the end, and if it's not, then it goes to loop begin. So this is the loop. And this is the original loop. Now look at the addressing mode here. RDX plus R9. RSI plus R9. So this is the base pointer of A in RDX, and base pointer of B is in RSI, and the base pointer of C is in RDI. So this is the one way, which is the slower way. And I call this no unroll version. It takes 1.3 cycles per iteration. So you have like these six instructions, but actually it takes 1.3 cycles per iteration. The second loop is that the loop the clock unrolled, and you see here I have 4 loads of A of I, then 4 additions of AI and B of I, and then 4 stores. And this sub is actually adding 128 to R9, so it increases increment by 4 times 32, and then it checks the condition and goes to the beginning. Now look at here. Originally I have here loads RDX plus R9, RDX plus R9 plus 32, RDX plus R9 plus 64, RDX plus R9 plus 96. And that is repeated same here and same here. Now this version here is about, so it's 4 cycles per 4 iterations on 1 cycle per iteration. Why? Why is this version faster than this one? And it's related to instruction dependencies, but not only that. Yes?
Because of the last 3 operations, which in the first version you have it in every iteration, and in the second you only have it in once.
So, okay, so that's the true. That's true because here I have a total 16 plus 3, 12 plus 3, 15 instructions here for 4 values. And here I have 1, 2, 3, 4, 5, 6. 6 times 4, it's 24 instructions, which is a drastic difference. Of course, I would expect that. But then I did a manual loop unrolling, and then I removed some compares and I removed some jumps. But again, I get 1.075 compared to 1. But this time the number of instructions is 3 instructions more. So this is on the, so this is side by side, but so this is what the Clang did, what did the Clang made, and this is what I made. I just repeated the body of the loop of the no unroll version 4 times, and I just removed these 2 instructions, compare and jump. But again, what compiler was generated, it was slower. No, sorry, this one is slower. This one is faster.
Yeah, so it's using 4 different registers, right? So there's no one register you're waiting on?
Okay, but why does it make it faster if I'm using 4 or I'm using 1? That doesn't.
You need to wait on its completing for every piece, right?
Can you explain again?
So on the right one, you're using the same register, so it needs to fully complete the block before it can continue with the next block.
Doesn't need to complete. Why does it need to complete this block before it? I mean, why does it? Okay, colleague said something like this: you cannot start this instruction before this instruction is this block is completed. But is it the whole block or just something from that block? What? The addition. So what happens? The addition has 1 cycle latency. And you can do this addition. There is a dependency chain of addition. So this addition depends on this one, and this on this one, and this on this one. What does that mean? You can execute 1 addition every cycle. So addition after addition. But each block can only start before the addition, before it was done. So you can start this and this and this only when this addition is done. And you can start this and this and this only when this addition is done. But what happens here? There is a dependency on R9 here, but you can do this instruction and this instruction and this instruction and this instruction in parallel. And when they're done, you can do these adds, and then you can do these stores. So you can, there is a little bit of advantage here because you can start things, 5 minutes. You can start things earlier here. But what was the price that you had to pay? It didn't come free. No. Yes?
I mean, you're paying the pressure on the memory subsystem again?
It increases because the code is faster. Yes, it does, but it's not the price that you had to pay. No, it's in the code. You see it. It's in the numbers. It's here. It's not hidden. It's on the screen. Sorry? Yeah, so the loading here was RDX plus R9, and the loading here is RDX plus R9 plus 32. So that's the thing. You have another addition. Somebody has to do this addition. It doesn't happen automatically. Yes?
Yeah, but isn't that usually a fuse instruction where it's basically in the instruction set baked in that you can do that, or is it really?
It costs something. Somebody does it. There is an additional circuitry. This consumes more power because you need to do more additions.
Yeah, but is it really in practice that they also will
No.
higher latency?
So earlier, the thing is that earlier this instruction had a bigger latency than this one, but in the last maybe 7 or 8 years they have the same latency. So they managed somehow to iron it out. So there is no difference between this instruction that does just one addition and the other one that does 2 additions. And actually, if you use LLVM MCA, you can see that. So this is the tool, and I'm going to show you just. It's a very nice tool. So this is the tool, and what it gives you, it emulates 100 iterations here, and it tells you how in 100 iterations I executed 600 instructions, and total cycles I needed 144, and the block throughput, reverse throughput, so I had to do 1.3 cycle per iteration. And then it gives you latencies for instructions. For example, it says that this addition takes 8 cycles, and so on. But it doesn't matter. This is the interesting graph here. So this is the emulation, how it goes. So these are instructions, and they just keep repeating because it's just running in loop. So this big D means dispatched. So it entered the CPU. And this E, minuscule E, so little e means it's executing. And the big E, and the big E, it means it is executed. And the R means retired, so it's done for the processor. And what you see here is that, what you hear said, this load entered and immediately start executed, and this one entered and immediately start executing. And this the third one, it didn't start executing immediately. So it was waiting for the data from these 2 previous instructions. And then you see here that the comparison entered and finished immediately. Jump was waiting a little bit for the comparison to be done, but then finished. And then you see here. So if you look at these graphs, and if you analyze it, you will see that you cannot start anything. You cannot start blocks here if this addition is not done. So I have add, compare, jump. And then you see this instruction, it entered the pipeline in the CPU, but it didn't start executing immediately. It started executing only when this instruction, the previous one, was done. Okay? Okay, so any questions?
What tool did you use to get that output?
LLVM MCA, it's mentioned here.
Okay.
There is actually, the last slide is the same tool, but you just use it on the Godbolt. And also, I can share the example here, and you can also run the tools and see how it works. Any other questions? Yes?
You showed that compilers can do some of that stuff on their own. How much is that dependent on specifying the target architecture?
I think this thing would be done most of the time. It doesn't even depend on that. So the LLVM has kind of scheduling model, and it knows that on certain certain CPUs, this addition costs more, so it can omit it or try to do different kind of optimization. So they can do that. LLVM can do that. Yes.
Do you have any practical guidance on using, basically, if you encounter a performance problem, new profile that you measured, you found out it's this section of code in a larger project. How would you go about applying those tools? Would you basically transplant that code outside so you have it for analysis?
For the LLVM MCA, you can use it like when you have up to, let's say, 50 or 100 assembly instructions. It doesn't make sense to use it for a bigger code. It doesn't emulate when the loads don't come from the memory caches and that kind of stuff. It doesn't emulate them, and it's not perfect, but it teaches you something interesting. You should have a mental model of. Okay. Yes.
Yes, there's no other question. So my question is kind of a structural one instead of the technical focus. I was wondering, so in your team or in your company, what is the structure about, integrating all that stuff? Like, is there a separate team focusing on this instruction level or maybe vectorization?
So I work on a Java compiler, so we are writing Java compiler, so we do use that kind of stuff. I mean, so it's LLVM-based compiler, so yeah.
I see. So, but depends on if we are talking about, like, I don't know if you are aware of any other teams that are working on the same level of optimizations. Like, imagine like a team is trying to
So for performance critical software, you should definitely know what's performance critical software depends on the domain. For example, in finance and high frequency trading, you have that, but like in regular finance, you don't, and it really depends.
Yeah, and in terms of best practice, what would you offer? Like
Best practice.
People working on the optimization stuff. Because there are a lot of levels of optimization, as you said, vector operations, caching, instruction level parallelism, and then all sorts of other things. And when it comes to the point of other accelerators like GPU or low consumption stuff, I mean, that's a QC. Yeah.
Let's stay after the talk and talk about it because it's open-ended and it can take a lot of time. And I need to do the advertisement now. So. I offer on 24th of November the AVX vectorization workshop, and there we will learn to use AVX intrinsics to speed up stuff. It takes place on November 24th and 25th. So for those people who don't know about vectorization, it allows you to process 4 or 8 or 16 elements in a single instruction. So a single instruction loads four integers and loads them to this register, and then another instruction loads another 4 integers and loads them to a second register, and then you have an instruction that adds these 4 loads and then stores them somewhere, store them to memory. Instead of doing them one by one, you're doing them in 4 by 4. And this is what AVX is all about. So AVX is all the Intel CPUs and AMDs have these. It's 2 days workshop, and it also covers ways to make the maximum performance. Among others, we talk not in this detail about instruction level parallelism, but what's important for vectorization. So we start from really basic stuff like compiler intrinsics, and then we learn how to vectorize loops, and then we learn how to write code that it has maximum performance. So it's not only vectorized, but it's very efficient. And we talk about memory optimizations. And if you're interested, so on the Meeting C++ side, there is a link on how to register. That's it. I run this Johnny Software Lab site, which is like I write a lot about software performance, and I do performance trainings. So AVX performance is this one that's happening in Meeting C++, but there are also other ones. The Neon training, which deals with Neon vectorization on embedded system on Macintosh. And there is also another workshop that I'm currently preparing called Memory Optimization Workshop. And we are working, it's again 2 days, and we're learning how to maximally use memory subsystem for performance. So it's not out yet, but it will be out by the end of the year. And yeah, that's it. Thank you.